Hello, so in this video we will talk about the concept of radical planes. So if we have the spheres S1 and S2 with their centers P1 and P2, then the spheres are and the equation of the sphere is given by this one, x squared plus y squared plus z squared plus some constant x, some constant y, some constant z, and some constant is equal to 0. And similarly for S2, then if we subtract these two equations, and then the equation we get is of a plane which is called the radical plane. Okay, so then the plane formed by subtracting these equations is the radical plane for these two spheres. Okay, and this equation is obviously given by, we can cancel out this and this, and these things cancels out and so on, and you will have a1 minus a2 x, b1 minus b2 y, c1 minus c2 z plus d1 minus d2. Okay, so now what is the normal vector for this plane? Normal vector is a1 minus a2 comma b1 minus b2 comma c1 minus c2 in a vector form. Okay, so now if we want to prove that this normal vector is parallel to the line joining the sphere center, how do we do that? Okay, in order to do that, we have to go to this equation, the starting equation, which is x squared plus a1x. So what I'm trying to do is I'm just combining the terms with x and y and z. So y squared plus b1 y plus z squared plus c1z plus d1. This is equal to 0. Okay, so now if I write it as a square, uh, some square, so I can say x plus a1 over 2 squared plus some constant, let's call it k1. Okay, so I can, or minus, I mean k1 can be negative or positive, that's not the point here. The point here is that I can write it like this. Okay, and similarly I can write it as y plus b1 over 2 squared plus some k2 plus z plus c1 over 2 squared plus k3 plus some d1. Okay, now you can appreciate that I can absorb this k1, k2, k3 into d1. So I can say x plus a1 over 2 squared plus y plus b1 over 2 squared plus z plus c1 over 2 squared. This is equal to some constant. Okay, so I can say this whole thing minus d1 minus k3 minus k2 minus k1 is my k here. Okay, now compare it with the general equation of a sphere. The general equation of the sphere goes like this: x minus x0 squared plus y minus y0 squared plus z minus z0 squared. This is equal to r squared, and the center is, so center, this is x0, y0 and z0. So this means the center of this guy is what? Center of this guy is minus a1 over 2 minus b1 over 2 and minus c1 over 2, correct? And similarly the center for the other one should be, so this is for S1, so center for S2 will be what? Minus a2 over 2 minus b2 over 2 and minus c2 over 2, correct? Okay, so this means the vector joining this center and this, so this is p2, I should say p2, and this is p1. So p1 p2 is what? P1 p2, this is equal to, so this is a vector here, so this guy minus this guy, correct? So I can say a1 minus a2 over 2 and b1 minus b2 over 2 and c1 minus c2 over 2. Okay, so this is just half a1 minus a2 b1 minus b2 c1 minus c2. So this means this is in the same direction because this is just a constant times this vector. So this means same direction as normal vector to the radical plane. Okay, so this means that this direction is the same as this one. So or we can say normal vector is parallel to the line joining the sphere's center. Okay, so this is the first part we have. Now we have to prove that if the spheres are tangent to each other, the radical plane is also tangent to both the spheres. Okay, so then what does it mean that spheres are tangent to each other? Spheres are tangent to each other mean that they touch only at one point. Okay, so this is the situation. In order to prove that this the radical plane is tangent to both of them, we have to prove two things. We have to prove that radical plane is normal to both radii. But we have already done it. We have already done it. Why? So we know that radical plane is normal to the line joining the center. Correct? We have already shown that. But the line joining the center, so this line joining the center, line already contains, or that line already contains both radii. So this means this statement is true. So the other thing we have to prove is, we have to prove that radical plane only touches the spheres at a single point. Okay, so then since these two circles touch at one point, so let's say a common point of S1 and S2 is, let's say it is x1, x2 and x3. This means it will satisfy both the spheres equation. So this means that x1 squared plus y1 squared plus z1 squared plus a1 x1 plus a2 x2 plus a3 a2 y1 or this is b1 plus a1 x1 plus b1 y1 plus c1 z1 plus d1, this is equal to 0, and I can also say x1 squared plus y1 squared plus z1 squared plus a2 x1 plus b2 y1 plus c2 z1 plus d2 is equal to 0. So now if I subtract these two equations, what do I get? I get a1 minus a2 x1 plus b1 minus b2 y1 plus c1 minus c2 z1 plus d1 minus d2 is equal to 0. Correct? But this is exactly the equation of the radical plane, right? So this means x1 y1 z1 is also on the radical plane. So this means it does not touch, the plane does not touch those two circles except at their touching point. Okay, so this means we have proved two things. We have proved that the plane only touches the two circles at their at the point of their touching, and secondly, that plane is perpendicular to the radii of both of them. So this means this plane is tangent to both spheres. Okay, so now we have proved it. Okay, now we want to show that if two planes intersect in a circle, then the radical plane contains that circle. Okay, so in other words, if we have this sphere and this sphere, so this is, if you imagine it in 3D, this is a part of the circle where uh, the intersection of this circle, the intersection of these two spheres occur. So what we want to prove is that this radical plane contains that circle. Okay, so let's say we have a point. So let's say again we have a point x1, y1 and z1. Okay, what is the property of this point? This is the property of this point is that this has is on the intersecting circle. So this means that x1, y1, z1 satisfies both spheres equations. So again, if we subtract those equations, um, we can say that, so this means if this is on the intersecting circle, this means x1, y1, z1 is on the plane, on the radical plane. Correct? So this is by subtracting. Same story. Okay, so this means now we started with this point. Any point which is on the intersecting circle is also on the radical plane. So this means, what is our conclusion? Our conclusion is that the radical plane contains the intersecting circle. Okay, so we started with any arbitrary point on the intersecting circle, and we proved that that point has to be on the radical plane. So this means radical plane contains the intersecting circle. Okay, okay, now this is a little bit tricky. Now we have three spheres, S1, S2, S3, and the radical planes are given by gamma 1 2, gamma 2 3, and gamma 3 1. And what we have to prove is all three planes are either parallel or they intersect in a single line. Okay, so let's talk about this parallel situation. So this first situation is, we have this circle, then we have, let's say, this circle, and then we have, let's say, this circle. So now note that if I draw a line from one center to the next center, it does not change direction when I use the third center. Okay, so we have this situation here. So this is my S1, this is my S2, and I'm checking it in 2 dimensions here. So the plane for S2 and S3 is if I see it in 2D, I see it like this. So this is gamma 2 3. This one is for gamma 1 2, and then maybe gamma 2 3 as 3 1, maybe somewhere here. Okay, okay, now note that what do we observe? Okay, so this is my P1 and this is my P2, this is my P3. Okay, so I can say P1 P2 and P2 P3 have same direction. This means that P3 P1 or P1 P3 is also have the same direction. Okay, I would say same direction, or uh, exactly opposite direction. just to complete it. As when I say exactly opposite direction, it means that one vector is like this and the other vector is exactly the opposite, but they are still parallel, right? So then p1 p3 also have the same direction or exactly the opposite direction, correct? So p3 p1 is like this. So this is my p3 p1, this is my p1 p2, and this is my p2 p3. So this is p3 p1, this is p1 p2, and this is p2 p3. Okay, so this is for just the demonstration purposes. Okay, we won't use it now. If this is the case, then this means, what is this? So r1 2 has this normal vector, so normal vector, because we have already seen that the line joining the centers is always normal to the plane. So this means this has normal vector of, this is the normal vector of gamma 2 3, and this is the normal vector of gamma 3 1. Okay, so since we can say, since normal vectors are parallel or in the same direction, this means planes are parallel. Okay, so this is the first part. Okay, now we have some tricky situation here. Now we have, so this is, we have said this one, and now we have to prove some other situation. Now the other situation is something like this. We have one sphere here, one sphere here, and let's say one sphere here. Okay, so this is my S1, S2, and S3. This is the center, this is the center, this is the center, and this is P1, P2, and this is P3. Okay, so this is the, you know, view for gamma 1 2. This guy is for gamma 2 3. What about this one? For this one we have to have this kind of a story here. So gamma 3 1 is this one. Okay, now you can, I mean, this is a very rough diagram, but you can see now just by drawing that they intersect in one point. So in 3D it means that they intersect in one line, but we have to prove it. How? We have to prove it mathematically. Okay, so what is the equation for the first plane? So first observation is that 3 is nothing more than 1 plus 2, and obviously times by minus 1. Okay, so my point here is the 3 is some linear combination of 1 and 2. Okay, this makes sense. Okay, okay, so this is the first thing. Okay, now if we have a situation like this, in which we have I'm doing some digression here. If you have a situation like this, if we have ax plus by plus cz plus d, this is equal to 0, and then we have some px plus qy plus rz plus s, this is equal to 0, and then we have, for example, a plus p, x plus b plus q, y plus c plus r, z plus d plus s, this is also equal to 0. Okay, now note that this minus 1 is there, but I can take this minus 1 out for everything and then absorb it in 0 here. Okay, so then if this is the situation here, then if we want to, so this is my, let's say this is my equation 4, this is my equation 5, and this is my equation 6. If I am solving this one, I mean, it takes some algebra here, but I can easily check that my x, and if I'm solving this one, remember I have two equations and 3 unknown, so I can say x is equal to 0. Assume what I'm trying to do is I'm trying to find a point on the intersection point of these two. Okay, so then if x is equal to 0, then my y is equal to minus dr plus cs divided by br minus cq, and my z is minus bs plus dq divided by br minus cq. Okay, now if this is the point on both these lines, it means this is the point in the plane r1 2 gamma 1 2 and gamma 2 3, then our question is whether this is the point on gamma 3 1 or not. Okay, so then what do? We put this point 0, this and this here, so we can say this becomes 0, and then we are left with b plus q times this guy minus dr plus cs divided by br minus cq, and then we can say plus c plus r, and then I can say minus bs plus dq over br minus cq plus d plus s. This is equal to 0. Now you can say you can do some basic algebra here. So if we do that, then we can say that this is actually equal to 0. This actually is satisfied. Okay, so what do? I mean, we don't have to do it, but we multiply by b minus br minus cq everywhere. So this goes, and this br minus cq comes here. Okay, and then once you do it, it's just a matter of multiplying properly and cancelling all the terms which cancel out, and you will see that they actually do cancel out. Okay, so what do we have to prove? What have we proved? So this means any point which is common to and the plane radical plane for sphere 1 and sphere 2 and radical plane for sphere 2 and sphere 3, it is also on the radical plane of sphere 1 and sphere 3. Okay, and also, is there only one point? No, there are multiple points, because we chose x to be 0. We can choose x to be something else as well, right? Then we get some other y and some other z, and you can easily check that this is also proved here. It will be proved. So we can choose any arbitrary point, and so this means also we have multiple points, multiple intersection points. Means for gamma 1 2 and gamma 1 3, or sorry 2 3. So this means all the planes, they intersect in a line. Okay, so as a recap, what did we do? We wrote the equations for the planes, and then we observed that this third plane is just a linear combination of the first plane. Okay, so this means any point which is common to both these points, both these planes, both the first two planes, is also present on the third plane. So this part is just algebra here, but this is basic linear algebra, that if the third equation is a linear combination of the first two, that any point which is common to the first two should be also present on the third should also satisfy the third equation. Okay, so then we said that there can be multiple points, because we chose one point x, and this is just two equations and three unknowns, so this has to have infinite solutions for all of our variables, as long as some singularity conditions are met. We are not interested in that part right now. Okay, so this means these three planes, they intersect in one line. Okay, so this is it for this video. Hope it was easy to understand, and thanks for watching. Hope you like the video.